Hello and welcome. In this tutorial, we will create a buffer slicer in Max. Okay, so before we start patching, maybe we should clarify what we're trying to achieve here. So I want to slice a sample into equal pieces or equal segments and then play them in a sequence to kind of put the sample in a new rhythmical context. So this tutorial consists of 5 parts. In the first one, we will just play the sample using gen. In the second one, we will create the sequence. In the third one, we will use the sequence to then control the playback of the sample. In the fourth one, we'll add a windowing function to prevent clicks. And in the fifth one, we will look at creative ways to come up with new sequences. So I will start with an empty max patch. First, I will create a buffer that holds our sample. So I'll use a buffer object. Let's call this one sample, and let's assign this to, let's use the Jongli file. And I also want to use a waveform object so we can visualize our sample. I will use a load mass to initialize it. So set sample, and now we can see the Jongli sample here. So then for the playback, I will use a gen object. Let's call this one Playback. No, that's wrong. Like this, okay. Let's also put the buffer in here. Let's also call it sample. And then I will assign it from the outside. So sample, this buffer here is going to take sample, this buffer here. This is maybe a bit redundant because if we're using the same name, then gen knows which buffer we want. But if you transfer this to Max for Live and you're using this dash terminology, this would still work. So using this, and then if I double click here, I can see that we're using the same buffer. So that's why I'm writing it like this. Okay. So now I want to play the sample at its original speed. So we can use the peak object to do this. So with the peak object, we can play the contents of buffers. So I have to specify which buffer I want to play. So it is the sample buffer. And I have to specify how we're playing it. So with this one, I want to use the index phase and I want to use linear interpolation. So index phase means that we're playing the contents of the buffer through the relative position. So we're coming in with a signal that ranges between 0 and 1. And so the whole contents of the buffer are represented by this number between 0 and 1. The other way to play a buffer would be to use index sample, and then we would play the buffer back by using the absolute sample. So the integer index of each sample within the buffer. But I want to use a phaser. I will just quickly use a scope to take a look at the phaser. So let's say we give this one a frequency of 1 Hertz. So we can see we get a ramp from 0 to 1 at a frequency of 1 Hertz. And this ramp can then play back the sample. But we don't want to play it back at a frequency of 1 Hertz. We want to play it using its original tempo. So to get the original tempo, I can take the left outlet, which gives me the length in samples, and then say that we're dividing the sample rate by what's coming out of here. Then we can plug. This essentially gives us the frequency, so we can plug it into the phaser. And now you can see it's much slower because it's the original frequency of our sample. And if I'm plugging this here, we should get a loop of the original sample out here. I will use the first inlet to multiply this by what's coming out of here so we can change the frequency. So if I'm multiplying this by, at the moment we multiply everything by 0, so nothing changes, but if I multiply this by 1, we get the original frequency. If I multiply it by 2, we get double the speed. If I multiply it by 0.5, we will get half the speed. So I will control this from the outside with a signal. I will plug this in here, and if we set this to 1, we should have the original playback speed. So let's create an easy DAC and use a live.gain so we can check if everything is correct. Let's plug this in here, plug those in here, and now we should be able to listen to it. Okay, so yeah, seems to be working. So this is the original speed, twice the speed, half the speed. Okay, great. So this seems to be working. So moving on to the second part of the tutorial, creating the sequence. So I want to use an object called multislider to create the sequence. I will first, how will I do this? I think I will first set the number of steps. So this integer, this number box will determine the number of steps. So I will send this. I will use a send object because we're going to need it in several different places, and so it's just cleaner. But first we need it here. So now the multislider is just one slider, but for each step I want one slider, and each slider should have as many steps as we have steps here. So how can we do this? I will first use this number of steps receive as an input. Then I'll use a trigger integer. And first we have to change the size. So the size determines the number of sliders we have here. So if I type in 8 here, we have 8 sliders here. And now you can see that I want discrete steps, but here we have a continuous float that's coming out here. So to change this, we can, where is it? Sliders output values, instead of float, we can say integer, and now we get discrete values, but only in a range from -1 to 1. But I want it in the range from 0 to number of steps -1. So here we're just saying 8, but here I will use the, what's it called, set min max, and then say the minimum is 0 and the maximum will be the number of steps minus 1, because in gen we will use this as an index, and it's just easier if it's ranging from 0 to the number of steps minus 1 instead of 1 to the number of steps. So I can plug this in here. Again, set the number of steps, and now we have steps from 0 to 7 and everything in between. So this is just a setup for the multislider. I want to copy the contents of this multislider into a buffer and then use the buffer inside of our playback engine as a lookup table. So how can I get the contents of this multislider into a buffer? First, I will create the buffer. No, not bug, but buffer. Let's call this one sequence. And then I will use the poke object to fill our buffer. Okay, first, before filling it, we have to tell it how many samples we want. So in this case, every sample of the buffer is representing one of the steps. So we need as many samples as we have steps here. So again, let's say we have 8 steps. We can take a look in here. So size in samples 8. So this is already working. Yeah, that's why I'm using the send and receive objects, because we'll need this number of steps a lot. So now, how can I fill this sequence buffer? What's coming out here is just a list of the content, but I want in the left inlet, I want the individual values, and in the right inlet, I want their index. So to get the individual values from this list, I can just say iter. So we can take a look at this when printing. So now we can see we're getting individual values out of this. But I also want to count the values, so I get the index. So I will use trigger integer bang. So out of here we get the values, and here we will bang for every, we'll have one bang for every value. Count them, put them in here. But the problem is we also need to reset the counter every time. So every time a list comes in here, so I will say trigger list 0. I'm resetting this. So what is happening? I'm changing something here. First, we will reset the counter. Then we will create individual messages out of this list. And for every individual message, we will bang this and get the index. So if I do something like this, we can then see this represented in our buffer. Okay, so this is how you can turn your multislider object into a buffer, or just transfer the contents into a buffer. So moving on to the third part, we want to use this sequence to play the sample. So I will do this in gen again in our playback engine. Here, of course, we need the sequence as a buffer, and I will also assign it out here. So sequence. So let's see if this worked. So if I'm double clicking on it, I'm getting the sequence. Okay. So what I want to do now is read the sequence. So to do this, I want to turn, I will use the second outlet to debug what we're doing. So now I'm getting a ramp from 0 to 1, but I want to read the contents of the buffer by their index. So to do this, I will multiply what's coming out here. So now we're getting a ramp from 0 to 1, then I'm multiplying it by the number of samples in the buffer, which should be 8. So now we will get a ramp from 0 to 8. So to visualize this, because here we're in a range from -1 to 1, we can see that we're now getting a ramp from 0 to 7. But as you can see, we're getting a continuous float output here. But what I want is just the integer part of it. So we can use the floor object that will just discard the float part of it and just give us the integer. So now that we have this, we can use another peak object to read or to playback what's in our sequence buffer. And this time, as I said before, we don't need the index phase, but we need the index that's called samples, because we're reading the contents by the actual index. So 0 would mean we're getting the first sample, 1 would mean we're getting the second sample, and so on. So plugging this in here, I'm getting an error because here we have a typo. So now it should be working. And now you can see if I'm setting everything to 1, we're getting constant ones. And if I'm doing something like this, you can see, and we're just playing back what's in here. So now I want to use the sequence that's coming out of here to control the playback. And I will do this by introducing a playback offset. So we will always play just the first segment if the offset is 0. If the offset is 1, I want to play the second sample. If it's 2, I want to play the third segment. If it's 3, I want to play the fourth segment, and so on. So first we need to find a way to just play the first segment here, because now we're playing the whole buffer. So to just play one segment, we can multiply what's coming out of here by the number of segments, which is just determined by the number of samples that are in here. So now we're going, instead of going from 0 to 1, we're going from 0 to number of segments -1, so from 0 to 7. So let's quickly listen to this. Yeah, it's way too fast because it's essentially 8 times the speed. But I don't want to go from 0 to 7. I always want to go from 0 to 1. So I'll wrap this between 0 and 1. And now listening to this, we're playing the whole thing very fast. And to get to our original speed, I can just divide this by the number of segments. So now theoretically, if I didn't make any mistakes, we're only hearing the first segment in its original speed. Okay, that seems to be working. So now the signal that's coming out here will just go from 0 to 1 divided by 8. So 1 divided by the number of segments. And now I can use the number that's coming out here as an offset. So this number is going from 0 to number of segments. So again, we want to be in the range of 0 to 1. So we have to divide this by the number of segments. And then we can use it as an offset here. Is this working? Yeah, it seems to be working. And you can recreate the original if you put this in this order. Because this means that we're playing the first segment in its original place. We're playing the second segment in its original place. But if I'm doing something like this, the playback changes accordingly. What we can also do real quickly is, so I want to visualize this real quickly. So here we're getting the normalized playback position, so between 0 and 1, and I can output this here. Use a snapshot object which takes in a signal and outputs a float. So this means that we're outputting a float every 33 milliseconds. So now we're getting the playback position. And we can then use this in combination with a slider object to see where we're at in the playback, but we have to change a few things. So first we need float output. The range should be 1 because we're in the range of 0 to 1. Then I will use the indicator here. Get rid of the background, also change the color of the indicator, maybe make it a bit thinner. And then we should be able to just overlay it here. And now we get a visual representation of where we are. Okay. Looking great. So this is the end of part 3, coming to part 4. Yeah, the thing is, this is already working and already sounding great, as you can hear. But imagine, I mean, it's not audible when we're using this percussive sample, but if we're using something like this one, you can probably hear that the jumping around is causing clicks because this playback engine is not aware of any zero crossings. So we're not just jumping to the next zero crossing, we're jumping all over the place, so this can introduce clicks. So to prevent this, I want to create a window function that then creates a fade in and a fade out to prevent the clicks. So every step or every segment in the sequence will have a short fade in and a short fade out, so we don't have any clicks. So to do this, I will create another buffer. Let's call this one window. And let's give it a fixed size of, I don't know, 1,000 samples. I will also use a waveform object to visualize our window function. Let's also initialize this with a load mass. So say load mass set window. So to create this window function, I want to use a sine function for fade in and fade out. So to do this, I will use an USI object and say 1,000. So what this object does is if I'm clicking here, we're getting numbers from 1 to 1,000 out of the right inlet as fast as possible. But I want numbers from 0 to 1,000 minus 1, so I'm using a -1 in between here. And then we will again use the poke object, say window, to fill our window function. So here we need the sample value and here we need the index. So let's use a trigger integer. I already know the index is going to be the number from 0 to 999. And now we can use the numbers that are coming out here to create our window function. So to do this, I will use a gen object. Just call it window. Plug it in here. Let's tidy this up a bit. So we know that we have a fixed number of samples here, which is 1,000. So I could just divide this by 1,000 and get a ramp from 0 to 1. So this should already be working. Beautiful. So every number that's coming in here from 0 to 1,000 or from 0 to 999 will be divided by 1,000, giving us a ramp from 0 to 1. Then if I then multiply this by pi and plug it into our sine function, we should get half of a sine wave. So 2 pi would be a full sine wave, but just pi would be half of a sine wave. Yeah, this could already be used as our windowing function because we have a fade in and a fade out. The thing is, we could also compute this in real time. So if I just use this directly in our playback system, it would also work, but it's kind of computationally expensive to calculate the sign of something on every sample. So it's a better idea to create this kind of lookup table and then read this buffer in here. So that's what we're doing. And you can also change this because this is quite a long fade in and fade out. So we could also use something like, I don't know, raising it to 0.5. So now it's a bit steeper, or let's go to the extreme and raise it to a power of 0.1. So now it's a very short fade in and a very short fade out. I think I will stick with that. So to use this in here, again, we have to declare or create a buffer, call it window. Again, I will also do this here. Let's say window is window. Let's put this here. Okay. Let's think for a second. Where do we need to apply this? Okay, I can still... Okay, I will change some things around. I can use the output 2 for our snapshot here, and the output 3 I will use for debugging now. So what do we want? We want a ramp that's going from 0 to 1 for every segment that we're playing. So are we getting it out of here? Let's quickly take a look. No, we're not getting it out of here. Because we're dividing it. What we want is the output of this one. Yeah, okay. So you can see that for every segment we're playing, let's make them a bit longer. So for every segment we're playing, we're getting a ramp that's ranging from 0 to 1. So I will then use this ramp to, again, playback this window buffer, say peak window. And here, again, we don't need the index samples, but we need the index phase because we're reading it as a relative position in the buffer between 0 and 1. So let's call this index phase. Let's also use interpolation. And now let's see if this is working. Yeah, so now you can see that with every segment we're reading the window. And if I'm changing something here, you can see that the window will change. Okay, but I think this short fade in is better. And now all we have to do is multiply the window by the sound that's coming out of here. And we should be good to go. So I don't need this debugging thing here. And now listening to it. No more clicks. So let's quickly recap what's happening here. So with this part, we're getting the original speed multiplied by a speed factor, so to speed it up or slow it down. We're controlling a phaser that gives us a ramp from 0 to 1. Then we're multiplying this ramp from 0 to 1 with the number of samples in the sequence, which represents the number of segments we have. So this will, of course, make it faster, and we're wrapping it between 0 and 1. So this will play the whole thing very fast or multiplied by a factor of the number of segments we're having. Then if I'm dividing it again by the number of segments, we will only get the first segment in the original speed. Then we're using the same phaser to create the indices for our sequence. So we can play back the sequence at index samples. Then we'll divide what's coming out of here, which will be an integer between 0 and the number of segments we have. We'll divide this again by the number of segments, so we'll have an offset between 0 and 1. We're then applying this offset here, because here we're only getting the first segment, but adding the offset will give us different segments, and then we're playing it back. Here we have our window function that is then applied to what's coming out. Okay, I hope this is clear. So coming to the last part of the tutorial, finding ways to fill this multislider, because it's very tedious. So imagine having something like 32 segments and then wanting to go back to the original sample. This is a very hard thing to do. So I will build something that will automatically fill this. So to fill this multislider, we just have to give it a list of numbers representing the slider positions. So to do this, we can again use the Uzi object. Let's put this somewhere here. So first we need the number of segments or number of steps. Then of course we need our -1 because we're starting at 1 here. And as we saw earlier, we're just getting individual, sorry, I need to reassign this. So we're just getting individual messages out of here. So we first need to group them. So we can use a setl group object. We also need to tell this object how many segments we have. How many items the group has, so to say. So again, let's say 16, and now we get numbers from 1 to 15. And plugging this in here should then, if I didn't make any mistakes, result in, yeah, the original sample. We can also use this. I'm running out of space here. So we can also use this logic to just plug in random numbers here. So instead of using the right outlet of the USI object, we can use the left one, which is just sending out banks and then say, give me a random number between 0 and the number of steps we have. Again, the number of steps. And then I don't need this -1. I can plug this in here and then we'll get nothing because I first have to send this. So, and then we'll get random numbers representing the steps, and we can put this in here. A bit more space here. Okay, yeah, something like this. And then I can get a random sequence instantly and put it back to normal. And you can also go crazy with this. So what about 256? Or doing something like this. Or going back to our original file, we can do some funky breakbeat stuff. Next steps could then be to create your own algorithms to come up with something in between, like the original sequence and complete randomness. That could sound interesting, but that's up to you. So yeah, I hope you found this useful. Thanks for watching.